In physics, a lot of rules are, well, they're more like guidelines. But then there are the sacred ones, the absolute bedrock that reality is built on. And right at the top of that list, you've got the laws of conservation. They make this simple, powerful promise. Some things in our universe can never be created or destroyed, only moved around.
So, what do these three things have in common? I mean, what invisible thread could possibly tie together the total chaos of a car crash, the beautiful precision of a game of pool, and the weird inner world of a single atom? It seems like they have nothing in common, but the answer? Well, it gets to one of the deepest truths in all of physics.
And the answer is just that. In any closed-off system, whether it's two billiard balls colliding or the entire universe expanding, certain things, certain quantities, have to stay the same, no matter what. This is the whole idea behind conservation laws, and honestly, understanding them is like having a cheat code for how reality works. So let's dive into one of the big ones, the conservation of linear momentum. And to really get it, we've got to learn the language it's written in, the language of motion. Okay, first up is linear momentum. Physicists use the letter P for it for reasons, but all it really is mass in motion. The equation is super simple. Just take an object's mass and multiply by its velocity. So a heavy bowling ball rolling slowly has way more momentum than a light ping pong ball flying at the same speed. Makes sense, right? And I love this quote because it just nails the concept. Momentum isn't some potential ability to move. It is the motion. It's the physical reality of how much oomph an object has right this second. Right. So if momentum is what an object is doing, how do you change it? Well, that's where impulse comes in. Impulse isn't a thing an object has. It's a thing that happens to an object. It's a force acting over a stretch of time, and its entire job is to change that object's momentum. This is probably the best way to think about the difference. Momentum is like your car's speed right now. It's a snapshot. Impulse is the act of hitting the gas or the brakes. It's the process that changes your speed. One is a state, the other is the action. And you have to get this difference because it's crucial for everything that comes next. Okay, so we've got the lingo down. Momentum, impulse, check. Now let's see this stuff play out in the real world, specifically when things get dramatic, when they collide. To really see these laws in their purest form, scientists have to create these perfect little worlds. They use amazing tools like this air track. See, the carts are literally floating on a cushion of air, which gets rid of almost all friction. It lets them see what's really going on with momentum when things collide without anything else getting in the way. And in these perfect little worlds, you basically see two kinds of collisions. You've got elastic ones where things bounce off each other perfectly, like billiard balls. Then you have inelastic ones where things get deformed or stick together, like in a car crash. In that case, kinetic energy gets lost as heat or sound. But, and this is the absolute key, it doesn't matter if it's a perfect bounce or a messy wreck, the total momentum of the system before the crash and after the crash is always the same. It is conserved. And this isn't just theory. This is physics saving your life. Think about a car crash. Your body has to go from 60 miles an hour to 0 almost instantly. That change in momentum, that impulse, is a fixed number. You can't change it. But what you can change is how long it takes. That's what a crumples-on does. It deforms, stretching out the time of the impact by just milliseconds. And because impulse equals force times time, if you make the time longer, the force goes way down. The impulse is the same, but you feel much less force. It's incredible. So, there we have it. Momentum is always conserved. Perfect, unbreakable, elegant law, right? Well, not so fast. It turns out that when we zoom way down to the quantum level, this perfect law starts to show a very strange crack. Yeah, this beautiful rule that works for everything from planets to pool balls, it runs headfirst into a problem that's been bugging physicists for 100 years. A problem that happens in the totally bizarre world of quantum mechanics. And it seemed to suggest that maybe this law wasn't so sacred after all. Okay, so here's the weird part. In the quantum realm, a particle can be in multiple states at once. It's called superposition. So imagine a particle that has a momentum of both +1 and -1 at the exact same time. But here's the catch. The second you try to measure it, the universe forces it to pick just one. So what happens if it picks +1? Suddenly, the total momentum seems to have changed. So where in the world did that -1 momentum just go? It looks like it vanished into thin air, breaking our most sacred rule. And for the better part of a century, the answer physicists gave was, well, honestly, it was pretty unsatisfying. They said that conservation was just statistical. If you did the experiments a million times, half the particles would pick +1 and half would pick -1, so on average, it all balanced out. But for any single individual measurement, the law looked broken.
But that just never really sat right, you know? A law that only works on average isn't much of a law at all. But just recently, a really groundbreaking paper has proposed a new solution, a secret ingredient that's been missing from the recipe this whole time.
And the solution, it turns out, is, well, it's one of those brilliantly simple ideas. The reason we thought momentum was disappearing is that we were drawing the circle too small. We weren't looking at the whole system.
The secret ingredient is something they call the preparer. This is whatever device, a magnet, a laser, you name it, that actually puts the particle into that weird superposition state to begin with. For 100 years, we figured that once the preparer did its job, you could just ignore it. That, it turns out, was a huge mistake.
See, the preparer and the particle are linked. They're quantumly entangled, so that lost momentum, it was never lost to begin with. The moment the particle is forced to choose +1, the preparer itself gets a perfectly equal and opposite kick of -1. The universe's books are perfectly balanced every single time. The law isn't statistical, it's absolute.
Okay, so what does all this really mean? This isn't just some clever accounting trick. It actually forces us to think differently about what conservation even is and what reality looks like at its most fundamental level. I mean, listen to what the authors of the paper actually say. They're arguing that the law itself needs to be rewritten. It's not about averages. The total amount of this stuff, momentum or whatever, is unchanged in every single measurement. Not just on average, but every single time. The sacred rule is sacred again. And this leads to a really profound idea. The preparer isn't just some piece of lab equipment. It's the frame of reference for the particle's very existence. A particle being in a superposition of +1 and -1 is meaningless in a vacuum. It only has meaning in relation to the thing that put it there. You literally can't define the state without including its creator. And that just leaves us with this one kind of mind-bending final thought. We started this whole journey talking about isolated systems, but if this is right, if every quantum system is forever linked to the thing that prepared it and the thing that measures it, what does it even mean for anything to be truly isolated? It suggests that at the deepest level, the universe is far more interconnected than we ever thought. And it makes you wonder, what else are we missing? What other truths are hiding in plain sight just because we aren't looking at the whole picture?